Um, Today is a fun day, I think, with respect to the tutorials, because we've kind of gone through a lot of the boilerplate cheminformatics things, processing molecules, filtering molecules, handling, doing alignments, generating descriptors, making QSAR models. These are sort of bread and butter things. The things that are more fun and still sort of under active development are a lot of the different ways of doing drug design. And this is also sort of where we start to get into the integration with Rosetta. And so I'm excited to start talking about that stuff today. So yeah, today we're gonna focus on drug design. The tutorial that you're gonna do first, tutorial number 4, is going to be about reaction-based drug design. And so reaction-based drug design, we're going to juxtapose with another approach called alchemical-based drug design. And there's a little bit of a history about why there's different ways, as well as different reasons to think about doing one or the other. Reaction-based drug design today, the tutorial will be BCL standalone, but we're going to start to talk about another approach using a different framework that will also be the one that we use for the Rosetta integration. And so I'm going to go ahead and start sharing my screen. So reaction-based drug design. And so, like I was saying, there's actually quite a few ways to do drug design in the BCL. And I've broadly split it out into these two sort of frameworks. And so we have the reaction framework in the BCL. The reaction framework was originally written by a graduate student named Alex Jeans. And Alex was a very talented grad student. He was very smart. He was very good at math and computer science, and he was an organic chemist as well. And so he split his time between the wet lab doing synthetic chemistry and the dry lab doing computation. And what he wanted to sort of build was a framework where you could write your own reactions and have the computer do them. And so Alex was also a C programmer, which for those of you who are a little bit familiar with programming, can lead to a particular style of programming. All that to say, the reaction framework is sort of unit. It's like a box. So if we want to do reaction-based drug design inside of the reaction framework, what that means is we really have sort of 4 classes that are sort of interdependent, that are really working with one another to parse something we're going to go through called an MDL RXN, or a reaction file. Convert that reaction file into an object that the BCL can understand, and then match the reactants and the products that the user from the reaction file to input files that the user provides, and then through a series of mappings create a product out of that. And so the reaction framework was designed as a very sort of standalone piece. It was just a chunk that was sort of supposed to always operate together. It was also primarily designed for ligand-based drug design. And so at this point in the lab, there was not a lot of, there was nothing complete yet with our conformer generator. We didn't really have any integration with BCL and Rosetta, and so we don't really have good ways of modeling protein ligand interactions super effectively in the BCL, especially not at that time. And so this was meant to primarily be used with 2D QSAR models. So 2-dimensional autocorrelations and scalar features and things like that. And so I will say, though, that the reaction framework is really, really cool, and it's got some really powerful things that it can do because it is customizable at the level of the reaction file. And so we'll talk about that in a little bit. That's primarily what you're going to be working with today. But I want to juxtapose that with the alchemical framework. And so the alchemical framework is, I guess, something that at one point in time, also Alex and another postdoc in the lab named Will Lowe had been interested in pursuing in the context of something called pharmacophore mapping. And it didn't really get off the ground. They tried to sort of build this process where you could have fragments that would grow off of the molecules, but they didn't really take it too far. And so I was lucky enough to have some time to go over to Bayer and spend about 7 or 8 weeks working on their main campus doing research with their computational chemists and cheminformaticians. And that whole experience was not just educational, but really left me with a strong desire to create customizable drug design tools that we could use to sort of do whatever we wanted with a molecule. And so the reaction-based stuff is great because there's a little bit more control over synthetic accessibility, synthesizability. You can be very direct about how you want to push something, but sometimes you just want to know, where am I supposed to put a fluorine, or am I supposed to have a ring here or a ring there? And you really just want to sample the chemical space, and you want to profile, and then you want to worry about everything else. And so the Alchemical Framework was sort of born out of that desire. And so instead of sort of pursuing some of the previous work that had been done in the lab, I made a new sort of interface called Fragment Mutate interface. And this is important because this is actually the class, the interface that Rosetta is going to make use of. And so I'll show you more specifically not tomorrow, later today, and then in the next session. I don't want to focus too much on the Alchemical Framework here, but the Fragment Mutate interface is essentially wrapped up in a mover in Rosetta, and then depending on how you initialize that mover, how you define it in your Rosetta scripts file or from whatever PyRosetta thing you're doing, that determines what type of behavior it has. And the Mutate interface is an incredibly modular sort of thing. And so it's an interface or a base class. And so there are a bunch of things that you have to define to make it qualify to be in this interface. But it makes it very plug and play. If you have a new way that you want to change a molecule, we can make that happen by putting in this interface, and then it will also have the behavior of a bunch of these other mutates. And so today we're going to start with the reaction-based drug design. I'm also going to show how a couple of the Fragment Mutate interface derived classes, so React and AddMedChem in particular, are really just sort of reaction-based methods that are almost AddMedChem, you'll find we can do really these one-shot reactions very effectively with it, and React, you'll find, is basically a mini version of the reaction framework that we've adapted to fit inside the Fragment Mutate interface. And so all of these things are things that we're actively developing. One of the things that I've been trying to do with both of these frameworks is allow them to be used for structure-based drug discovery. And so the Alchemical Framework was designed with structure-based drug design in mind. We want to be able to do ligand-based or structure-based. It doesn't matter. And there's some considerations we make for that. The reaction framework was designed with ligand-based drug discovery in mind, but we've been trying to patch it to make it amenable to structure-based drug design as well. And so yeah. Before we keep going, the idea with the reaction framework is that you'll create an MDL RxN file, and I'll show you those on the command line. I use Marvin Sketch for these from Chemaxon. It's free for academic use. You can use other softwares to draw these types of files like ChemDraw or BioVia or something like that. But the idea is you take a series of reagents. And so in this particular case, I have sort of goal for you guys at the end of the tutorial today, which is this split Ugi diamine 4-component reaction thing that I only know the name of because I've looked it up. And so the idea here is that you can specify, like, okay, I've got a piperazine ring, I've got, in this case, some sort of aldehyde that I'm going to have. Over here, I've got some type of carboxylic acid, and then I've got some type of isonitrile. And then over here, you've got a product, and you don't have to just have one. You can have 2 or 3 or however many you want. But the important thing is that the product has its atoms matched back to the reactants. And so the way that the code really works is that it takes a bunch of input files and input reagents. It tries to identify all of the different combinations in which you can combine those reagents such that they match this sort of pattern right here. So matching all of the reagents. And and for any single one of those cases where you have a reagent that can match all 4 of these cases, it will then produce a product by mapping the corresponding atoms to the structure over here. And there are cases where what's really cool about this framework is you don't actually have to have every single atom mapped. And so you'll notice this carbonyl group right here, or amide carbonyl, whatever it is. This thing does not have a mapped atom. We can just, and it's not that, it comes out of nowhere. It's just that there's some other aspect of this reaction that is not being completely captured, right? Like we're computational people. We can skimp a little bit on the details because, we're just trying to get the computer to mimic something that looks like real life. So that way, if we were to do this reaction, make a bunch of products, our friends in medicinal chemistry could go ahead and be like, oh, okay, I think we can probably put something together like that produces, these products. And so it's meant to mimic reactions. And so yeah, sometimes you've got very complex product scaffolds that form that are not even represented in the reagents. And really what the reagents do is just tell you how things are substituted off of those scaffolds. And so this is sort of the key sort of unique thing about Alex's reaction framework, and we've extended it to make it able to handle multi-component reactions like the one shown. And so unlike a lot of the two-component or one-shot style reactions, you can really create some very elaborate new substructures or scaffolds using these types of approaches. That being said, these are less amenable to having vendors and made on demand type compounds synthesized. And so there's a trade-off that you have to think about when you're figuring out what type of reaction system I want to use. So, what does this look like with respect to, this is a picture, right? The actual file format looks like this. And for those of you who have gone through tutorial 1 in its entirety, you were introduced to an SD file or a structured data format file. If you hadn't seen that before, an SDF. And the MDL-RXN file, or the reaction file, is really very, very similar to the SD file. And we're going to go ahead and not spend too much time on this. This is a truncated file. The whole file is in your tutorial. The thing I just want to point out is that essentially what this whole method boils down to is building these types of files using whatever type of software you want to then go ahead and run a reaction. And then this file format should be very familiar to you. Okay, so that's the few little slides we have. But what I wanted to do is take you through and just look at a couple of things. And so, can you guys see my terminal okay? Is the font big enough? Yeah, cool. All right, you can see me trying to figure out my other stuff. I'll actually do one more. Yeah, okay. So you can see that I am in tutorial 4, and I am in the 4-component reaction section of tutorial 4. There are a bunch of reagents in this file. We'll get to those in a second. The first thing I want to sort of look at is, if you want to do reactions, where are the places where you might look in the BCL to do reaction style drug design? And so the 2 apps that you'd probably be interested in are Molecule or maybe ChemInfo, are the 2 places where we would be actively developing algorithms for this type of thing. And so let's just go ahead and do Molecule, and we'll do help. And on Molecule help, we can see that we have Molecule React. We've got an older version of Molecule React. And so notice this one does not have a description. This is probably not part of the release, but Molecule React would be part of the release. It's obviously in development, just like pretty much all, Rosetta code is in development, but it's good enough that people can use it for real things, and so we release it. Let's see, we also have Molecule Mutate, which we'll take a look at shortly as well. So Molecule React, Molecule Mutate, both of these things talk about how you can modify molecules with them. All right, and let's see, I don't remember if there are actually anything in ChemInfo that we're using at the moment. I've got some alchemical things in here. Evogen is a evolutionary algorithm that uses reaction-based drug discovery to build products and grow sort of populations. This is also something that Alex wrote. It was his primary application for doing drug design with single shot reactions at the time. We don't use it as much for the multi-component reactions. We usually enumerate or do random selection on those, or perhaps even a Monte Carlo metropolis sampling, even though it's not true Monte Carlo metropolis, just because with the multi-component reactions, the thing you get out at the end is pretty much the end. You don't want to have to link together, 7 or 8 reactions that are single shot reactions that have to functionalize at every step and whatnot, quench them, things like that. Focused library design is an alchemical optimization algorithm. There were several iterations of this, and we've sort of wholesaled it and are redoing it. And then reaction combi-chem is pretty much what it says it does. It does reaction-based combinatorial design, but a lot of these apps we're not going to worry too much about. Actually, the things in ChemInfo have QStar models built into them, and so they do scoring as well as design on the fly. The things in Molecule just do sampling, and then we score afterwards. And so that's sort of the major 2 differences between these application groups. And so one of the ways in which we can start doing design, and probably the way I'd recommend, and what you're going to do in the tutorials, is just starting with Molecule React before we get anywhere else. And so in Molecule React, we pass starting fragments, which in this case, and actually I'll show you, we've got a piperazine, just like the one I showed you. And I'm going to start just with these demo reagents. And so I've got starting files and demo reagents separated. So I'm going to use my piperazine as my starting reagent, or my starting molecule, whatever. And then I've got all of these other things. I've got a formaldehyde, I've got this carboxylic acid, and a bunch of other carboxylic acids. And so some of them are more complex than others, but the point is that's what we've got in this file. And I think we've also got somewhere in here some isonitriles. You'll notice the isonitriles in, oh, I lost it. We need the isonitriles to work this thing. Let me go to the end. So this is an example of one. This has the resonance state that does not have a Zwitter ion, just because we don't have the carbanion version of that in the BCL, although I'll probably add it sometime soon. And so in this file, you can see in the reagents file, we had a formaldehyde, we have a bunch of carboxylic acids, and we have a few of these isonitriles. And so that's 3 out of the 4 reagents. And then in this first file, we have just the 1 piperazine. And so the reason why I split out the piperazine is because I want this to be sort of my reference position in real space. If we were to try to do structure-based design with these, we would want to try to reference these as the anchor regions in space. And that'll make more sense as you go along. It's also just, and we talk about this in the tutorial as well, so I'm not skimping on too much information. I'm just sort of giving you a preview. I'm suggesting that you can gain some control over having 2 separate ways of passing reagents. If you really wanted to, you could just, have the 2 same files, the reagents demo, like, cat this with this, and then pass them in both places, and you would try every single reagent in every single position, and it would be great. Okay, anyway, doesn't matter too much. The next thing we specify is the product. I have a reactions directory. And so let's go into the reactions directory. I use msketch, and I can take a look at my split uki diamine. All right. And so I see this one. I've got my piperazine. Let's see if I don't think, oh yeah, let's make this bigger here. This is very similar to the one I showed you on the slide. It's not the same, but it's similar. More directionality right here for this part, but this is it. And what you do is you can essentially say, oh, I want to map my atoms a particular way. Maybe this is not really how this happens, but maybe you want to say this oxygen actually maps to this oxygen. You can go ahead and add it. Definitely don't do that because that does not map there. But yeah. All right, so let's just run it. I've got a conformer generator here as well, because we're going to go ahead and do a ligand-based drug design run, and so we need to specify some options for conformer generator. But I don't have this file. Where'd it go? Oh, I'm in the reactions bin. There we go. So we'll run it. And we used a random seed, so I have no idea what's going to pop out of this thing. And what do we got? Okay, and we got something that looks like this, which looks like a real molecule to me. And yeah, so notice we've got our piperazine in the center, and our piperazine, oops. Oh, we did ligand based, that's right. So it's not going to preserve the piperazine core. And we walk through trying different examples of each for both of these. And so yeah, let's run another one. You know, we can do. And right now I'm using the random react mode, not the enumerate mode or the exhaustive mode. And so this was just going to randomly pick one of the valid reactions that I can perform to go ahead and do. And so look at that, we've got another one. So that's pretty exciting. The reagents are just some small sub-selection of some reagents I already had. But this is the general idea. And so we have the ability to put these pieces together, you know, to mimic reactions. And so the next step really for anybody who's interested in this is just to say, how do I want to sample those reactions? How do I want to do the design? And so there's lots of different types of space search, you know, optimization algorithms that you can design using the underlying code that does all of these things. And so right now in the tutorial, you're just going to focus on the sort of enumerative and the random style reactions. But we have other algorithms that are in development, and there's a bunch of people doing some cool stuff in the Meiler Lab for other types of sampling approaches. So, yeah, that's it. I don't want to take up too much more time. I can answer any questions if anybody has any. Otherwise, let's have you guys get started on the tutorials.
Hey, Ben. I just had a question about like scoring, and when you're sampling, what are you trying to optimize in a reaction-based drug design where you don't have a binding pocket per se? Just like, what are the different options? And you talk about like, oh, we can try different sampling methods, but what is the algorithm actually looking for?
So the reaction that I showed you just now, all that is doing is building a molecule from a pool of reagents and a reaction file. And so that is not scoring anything, it's just building it. The only score you're going to have is a conformer score for the thing that comes out. If you wanted to do drug discovery with that approach, the ligand-based way of doing it would be to say, do I have a QSAR model or a pharmacophore model or a similarity score or some other pose independent metric? And then as you're designing the molecules, you can score them based on selectivity or, you know, applicability domain or whatever you care about. And based on that selectivity score or probability of being active or whatever it is, you can say, do I want to make this or do I not want to make this in the lab? Yeah. So QSAR or whatever, something like that. Good question. All right, go get started. I'm gonna hang around, you know, you guys can chat in Slack or chat wherever, but the next talk, we're gonna get into the alchemical framework, so let's do a little bit of reaction-based design first. Thanks, guys.